Before a single bar of soap reaches supermarket shelves, before fragrance, branding, or packaging, it begins in a place few consumers ever see: industrial rendering plants. Here, animal byproducts, bones, fatty tissue, and trimmings are transformed into a crucial raw material: purified fat. Soap, at its core, is chemistry, and chemistry begins with molecules, specifically triglycerides. The molecular building blocks stored inside animal fat. Animal byproducts arrive under strict regulation. These materials are not waste. They are lipid-rich biological resources. Fatty tissues surrounding bones contain long-chain fatty acids, palmitic, stearic, and oleic acids. These fatty acids are essential for soap hardness, lather structure, and cleansing strength. Without them, traditional solid soap cannot exist. At the microscopic level, animal fat is made of triglycerides, 3 fatty acid chains bonded to a glycerol backbone. Why does this matter? Because soap is created when these triglycerides react with a strong alkali. This reaction, called saponification, breaks the molecular bond, freeing glycerin and converting fatty acids into soap salts. This chemical transformation is the foundation of every traditional bar soap ever made. To extract usable fat, the raw material is heated inside rendering vessels at temperatures exceeding 120 degrees Celsius. Heat melts the fat, separating it from bone and protein. Mechanical agitation ensures uniform melting. Why heat? Because fat is solid at room temperature. To isolate pure lipid content efficiently and prevent bacterial contamination, thermal rendering is essential. Once liquefied, the mixture enters high-speed centrifuges. These machines use centrifugal force to separate fat from water and solid residue. This step is critical. Impurities would weaken the soap structure and affect shelf stability. What emerges is tallow, a purified fat rich in saturated fatty acids. Before entering soap production, the fat is analyzed. Technicians measure fatty acid composition, moisture content, and impurity levels. Why such precision? Because the balance of stearic and palmitic acid determines hardness, melting point, and lather stability. Soap is not guesswork. It is controlled molecular engineering, from bone and tissue to purified lipid. The journey of soap begins not with fragrance, but with fat chemistry refined to precision. Next, this purified tallow will meet its chemical counterpart, sodium hydroxide, and when they combine, a transformation begins. Purified fat alone cannot clean. To transform it into soap, it must react with a strong alkali, sodium hydroxide. In industrial production, sodium hydroxide is carefully dissolved in water. This step is not simple mixing. It is an exothermic reaction, meaning it releases heat. Temperature control here is critical. Too much heat can destabilize the reaction. Too little can slow it down. When sodium hydroxide dissolves, ionic bonds break apart, releasing thermal energy. This heat is carefully monitored because it will influence the next phase, saponification. Industrial sensors track temperature and concentration continuously. Precision ensures predictable chemistry. Inside sealed reactors, molten tallow is introduced. Then, under controlled flow rates, the alkali solution is added. This is the moment the transformation begins. The environment must be tightly controlled. Temperature near 95 to 100 degrees Celsius. Steady agitation and consistent chemical ratios. Mechanical agitators rotate continuously, ensuring uniform mixing. Why is agitation essential? Because chemical reactions depend on molecular contact. Without even distribution, some triglycerides would remain unreacted, weakening the final product. Industrial mixing ensures complete conversion. At the molecular level, triglycerides break apart. The bond between glycerol and fatty acid chains is severed. Sodium ions attach to those fatty acids, forming sodium salts, the chemical structure we recognize as soap. Glycerin separates as a natural byproduct. This is the exact moment fat becomes soap. As the reaction completes, the mixture thickens. What began as liquid fat and alkali becomes a dense soap paste. The texture changes because the molecular structure has changed. The material now contains soap salts suspended in a semi-solid mass. Because glycerin is denser, it separates from the soap mass. In many factories, it is removed for refinement and later use in cosmetics or pharmaceuticals. Separation improves soap stability and allows precise moisture control in later stages. The chemical transformation is complete. But this soap paste still contains excess moisture. To shape it into solid form, water must be carefully removed not by simple evaporation, but through engineered thermal control. Next, the paste will enter one of the tallest structures in the factory. After saponification, the soap exists as a dense paste, chemically complete but structurally unstable. It contains too much moisture to be shaped into a durable bar. To stabilize it, water must must be removed with precision. And that happens inside one of the tallest and most energy-intensive structures in the factory, the spray drying tower. Powerful pumps force the soap paste upward to the top of the tower. Pressure is carefully controlled. Why? Because consistent flow ensures uniform droplet formation during atomization, and droplet size determines drying efficiency. Too large, and moisture remains trapped. Too small, and particles become brittle. At the top of the tower, a high-speed rotary atomizer spins at thousands of revolutions per minute. The thick soap stream is flung outward, breaking into microscopic droplets. This process is called atomization. The goal is simple: increase surface area. More surface area means faster evaporation. Simultaneously, heated air rises from the base of the tower. As droplets fall through this upward current, moisture evaporates mid-air. This is not simple drying. It is controlled thermodynamics, balancing air velocity, temperature, and humidity to remove water without degrading the soap's molecular structure. As water escapes, the droplet solidifies from the outside inward. This creates a porous internal structure, light, dry, and mechanically workable. The internal porosity is important. It allows later compression during milling while maintaining structural flexibility. What reaches the bottom are dry granules known as soap noodles. These particles contain carefully controlled moisture, typically between 12 and 15%. This range is critical. Too dry, and they crack under compression. Too moist, and they deform during shaping. Each batch is tested. Moisture analyzers heat small samples and measure precise water loss. Only when the target range is achieved does production move forward. Moisture control here determines durability in the final bar. The soap is now chemically stable and physically dry, but granules cannot be sold. To become a solid bar, they must be compressed, refined, and structurally bonded. Next, mechanical force will reshape these particles into uniform mass. At this stage, the soap exists as a concentrated liquid slurry, but liquid soap cannot be milled or stamped into bars. To create a stable, solid form, we must remove most of the remaining water carefully and uniformly. This is where the spray drying tower becomes critical. Instead of evaporating water slowly in trays, which would cause uneven drying and structural weakness, the slurry is atomized into microscopic droplets. By dramatically increasing surface area, water can evaporate almost instantly, transforming liquid soap into dry, porous particles engineered for strength and processability. Before atomization, the slurry must be pressurized. High-pressure pumps force it upward into the top of the tower. This pressure is not just for movement. It ensures proper atomization. If pressure is too low, droplets become too large and dry unevenly. If too high, particle structure becomes fragile. Precision pressure control determines final particle density.